Hi, everybody. Good morning. Welcome to the Molecular Device webinar on Axon Conventional Electrophysiology. My name is Jeffrey Tan, and I'm the product manager of Axon Conventional Electrophysiology product and market devices, and I will be your host today. Today's agenda is I will talk about the introduction of pCLAMP software for about 15 minutes, and Ed Rader, our application scientist, will talk about introduction of the Metamorph software, and he also will talk about to synchronize of both software for your recording. Now, before we begin, let me invite you to submit questions using the Q&A window on the right-hand side of your screen. To access the Q&A window, while in the full screen mode, locate the icon tray in the lower hand corner of your screen and click on the icon with the question mark. It's here. In the question mark window, and you can type in your question and press the send buttons. Any question that we do not get to will be answered privately in a follow-up email message. Now, let us start our presentation. So my part is talking about the introduction of pCLAMP software. So this slide shows all the products in the Axon Conventional Electrophysiology family. We have the pCLAMP software, which is a data acquisition and analysis software. And we have Digitizer 1440, which is an analog to digital converter. We have three types of pCLAMP amplifiers: ExoPatch 200B, Multi-Clamp 700B, and ExoClamp 900A for different recording applications. Now, these three components just work together as a system. Is that the amplifier is used to acquire biological signals, for example, currents and voltage, and send analog signals to the digitator, where it converts analog signal to digital signal. And the digital signals will be acquired and analyzed in the pCLAMP software. And then you can use our instrument for the following application, for example, the voltage clamp, wholesale voltage clamp, current clamp, 2 electro voltage clamp, intracellular sharp electro recording, and discontinued clamp, and also extracellular voltage clamp recording, as well as like electrochemistry and also nanopore study, and also bilayer study too. Now today, I just will talk about a brief introduction about pCLAMP software. The pCLAMP software is one of the most widely used electrophysiology data acquisition and software and analysis software. And pCLAMP software have three components. One is CLAMPX for data acquisition, CLAMPFIS for data analysis, and Exoscope is additional software that you can use to record your data in parallel with the CLAMPX. And why people like the pCLAMP? Because it is easy to use. Now I will use a few following slides to talk about some key features in CLAMPFIT and also in CLAMPX. For the CLAMPFIT, we can use you can have analysis. For example, you can plot the histogram, fitting, filtering, and power spectrums to analysis noise. And also we have some statistics. For example, ANOVA. We can also have a chi-square, and also we have student t-test and KS test too. We also have event detection, for example, Minis analysis or single channel analysis. Except for that, for the CLAMPFIT data analysis, we also have some data conditioning. For example, you can have trace, average the trace. You can combine the trace together. You can normalize the trace. You can subtract the trace, and also you can do some calculation between these two traces, and you can do baseline adjustment. You can also reduce the data point, and then you can also force some values to your data trace, and also you can move or shift the peak of data point also. Now, this slide just covers some key features for the CLAMPX data acquisition. We have online statistics that you can online measurement, for example, the slope or the peak of the current, and then you can also have the stimulus files and user list, and membrane test between suites, and also you have sequencing key that can help you to run a series of protocols together. And we also have a very use-friendly protocol editor, and we also have LTP assistant, liquid junctions calculation, and we also offer several recording mode. For example, people use a lot of episodic stimulation, gap-free mode, and also with fixed link events, we offer several recording mode. And we also offer the trigger external device through digital output. And we talk about that, how we can synchronize of the Metamorph. And we also in the pCLAMP, we also have like PNN list subtraction, P-sweep strings, right? But today, I cannot go through all those details for each key features, and I will focus on these 5 key features for the campus data acquisition. And at the end, I will also have the live demonstration to talk about the online statistic and the user list, because I think user list is one of the most, I think it's very useful feature in the CLAMP, but not a lot of people know about this. Now, online statistic. Now, online statistic is that you can use it for online measurement for various parameters of evolved events, such as peak of the current, or slope, or area of the rise time or decay time during the recording. Okay, and this mode and these features is only available in episodic and oscilloscope modes, and you can search up to 8 search regions, okay, for measurement of this peak of slope of the area. Now, this slide just give you an example, is that we have an outward signal, we have an inward signal. For example, for the outward signal, example is the excitatory postsynaptic potential, or inward signals like excitatory postsynaptic currents, population spike, or field EPSP. Now, people are interested to the peak value and also to the slope of this event. Now, by using the online statistic, now this slide just show you a simulation that we'll have this inward signal, and we will continue to measure for the peak and for the slope. Now, this is the right-hand side. You can see there's 2 profiles, one for the peak current and the slope that across the time. Now, for the baseline, okay, you can see the peak current and the slope. And after you can give any treatment, for example, you can give a drug or you can give a high-frequency stimulation, then you will see the peak current will be increased, and that the slope will also be increased. That you can see that you can see the change of the current, peak current, and then the slope across the time. That's what we call the online statistic. Now, this is the actual data that we see in the CLAMP. So this, like for example, is the EPSC. That you can see there's the peak current here, at the baseline, and this after the treatment, and then this is for the slope, and this is the baseline, and it is after the treatment, right? You can see that you can see at the same time during the recording. Now, how you can get this one? You can go to the CLAMP under the acquired at the protocol. And then you can see at the protocol under the statistic. Now you can see there's a variety of the measurement. For example, the peak amplitude. You can also the time of the peak, area, half time, slope, and you have the several regions. That the search region can up to 8 search regions. Okay. Now I will have the live demonstration at the end of my presentation. All right. Now, Stimulify, and this is also a very useful feature, that you can use this one to create your own waveform or import a wanted waveform. Okay. Now, if you are familiar with our pCLAMP, or you're familiar with how to create a waveform, now in the pCLAMP under the waveform, we already have some default waveform that you can use. For example, we have step. Okay, you can give a step voltage. We have the ramp. You can give a ramp voltage, and you can give a pulse train. And also, you can give a biphasic train, triangle train, or cosine train. But what happens is that if I want to create my own waveform. For example, we can create your own waveform by importing one of the trace. For example, in this case, it is an action potential traces, right? So basically, you can use the stimulus file to import the wanted trace as your waveform. Like I said, the waveform can be from your previous recorded ABF file. For example, if you in a current clamp you record a action potential that you can import the action potential trace to this as a waveform, and also the waveform can be artificial. You can make your own waveform artificially. You can create your own mathematical equation, or you can use or manually add it in for example, in the create a data function in the clamp fit, or you can use an Excel file. You can create your own waveform. Now, user lead is one of my favorite features that I want to share with you. That the user lead is to provide a way to customize your one of the range of the analog and digital output features. I have the live demonstration at the end of my presentation. You easily see it. It's very useful. And basically, after you use the user lead, it will override the generalized setting made elsewhere in the particle editor. Okay. Now, the user lead is that you can select a range of the parameter offered to configure on a sweep by sweep basis. And these functions allow you to set specific values for each sweep in a run. And you can also set a sequence of values and have this repeat. Okay. Now, this slide just gives you an example of how does it mean. Now, you can change the epoch, the holding level. It's based on your setting. For example, in the sweep 1, you can set to -50, and in sweep 2, you can set to 65 millivolts. Just give you an example. Okay, the first sweep, and the second sweep, and the third sweep, and the fourth sweep, and the fifth sweep. Now, it shows you an example in which you can set the arbitrary delta values for the waveform holding level. Okay. Now, we can also change for the holding level. Okay. Okay, the holding level, and have it repeated. Okay, you can -20 and 100 millivolts and have it repeated several times. Okay. Now, we can change the epochs duration. Okay, for example, in the sweep 1, 22 milliseconds, sweep 2, 44 milliseconds, sweep 3, 400 milliseconds, and sweep 4 for the 75 milliseconds. Again, just like you can set your arbitrary delta values for the waveform sweep duration. And just this gives you another example. You can repeat this for many times as you want. Now, this slide shows you the parameter that you can change. Now, I show you is that so we can change the voltage. We can change for the holding level or the duration. Right, this I showed you before. Change the level, duration, and then you can also change for the digital pattern. And then you can also change for the change, for the change period. Okay, or you can also change for our digital inner sweep holding level. Those are parameters that you can change in the user list. Now, where you can find the user list is under the stimulus file, user list, and all those parameters can be changed, can be found in here. And I will show you in the live demonstration about this after my presentation, about maybe about 5 minutes later. Now, this just give an example, a list of parameter values. When you get to for example, when you get to here, you click one of the parameter you want to change. Now, this is the parameter that you want to change for the epochs A level. You can type -50, 65, -20, 100, and then 29. This is for the sweep 1, sweep 2, sweep 3, and 4 and 5, and so on and so on. And you can also change the epochs duration. This give you an example: 22 milliseconds, 44, 100, and 75. Okay, that is the way that you can customize your sweep traces. The next one is, of course, sequencing key. The sequencing key is that allow you to associate several events as a sequence of events. For example, you can associate the digital output or change the holding level, or you can also associate with the memory test where you want to run the memory test or load the protocol. Okay. Now using the sequencing key to link one event to another, just like you run an experiment in an automatic fraction. You can run after you patch a cell, you can run a series of protocols without stopping the CLAMP. Now the sequencing key that you will use, now we assign some keystrokes. Okay, for example, auto 0 or control 0 to control 9, auto 0 to auto 9. So we have 50 keystrokes that you can use. Okay, so therefore this 50 sequencing key can be triggered in one time. Now, this is an experiment. This slide shows you an experimental design. For example, you run a memory test, protocol A, protocol B, and C, and memory test. Then you end experiment. Now, originally, what you would do is that you run the memory test, and then you run the memory test. So, and then you stop the memory test and switch to the protocol A, and then you stop protocol A, switch protocol B, and so on, right? So you need to stop so that you need to switch another protocol. But if you're using sequencing key, what you need to do is that you assign a keystroke, control 1 for the memory test, and then control 2 for protocol A, 3 for the protocol B, control 4 for protocol C, control 5 for memory test. What you need to do is that you just hit one keystroke, control C. Okay, for example, control 1. You click control 1. Now it will automatically run for you. Okay, it will go to the protocol A and B and C and then another memory test. They will end the experiment. So this is the way that it can allow you to have a automated fraction of the running of your experiment. Now this is the sequencing key dialog that you can set up the control 1, go to control 2, control 1 is memory test, control 2 is a protocol A, and then after that go to control 3. So I also have a demonstration to you after this, right? So I think I've run out of time, so that I would like to switch. I will skip this one, and I will go to the live demonstration to show you how to to use the statistic and the user list, and also for the sequencing key. All right. Now here is the CLAMP. I think people are familiar with this one. Okay. Now let me show you some online statistics. Okay. Now you need to go to the first of all, you need to go to you can go to the acquire, and then you can go to edit protocol. Now statistics is in this tab. Now you can check these boxes, and then you need to, for example, I'm interested to measure for the peak amplitude. I want to measure for the rise slope, 10% to 90%. Okay. Now, in order to do that, I want to simulate some data. Okay. Now, what I want to do is that I want to 0, 0, and I have a step here, and I give a 100, and then give 5 here. Now, I give this the protocol is that I have a 100 millisecond baseline, and I will have a 100 millivolt depolarization, so that when I go to the statistic, I know that the baseline will be in the first 100 milliseconds, and I will set, for example, I can say 40 to 50 as a baseline, and then the search region, okay, I will use because I know that the event will come in 100 milliseconds. I will set 90 to 120, and I hit OK. Now, when I do this one, and then you will see, okay, now you want to see the online window also, right? So let me set up the online window here. Right, online is here. Right, let me see this one. Right. So right now you can see, let me run more time, okay? So let me give longer, more sweep, and that is 1 millisecond. So let me hit this one. Now you can see here that it's online measurement for the rise slope, but of course you don't see the peak current because the peak current right now is about 5,000, right? So you can see here. You will see that. You see the 5,000 here, right? So that is what I'm saying, that you can do this online measurement. And of course, let's pretend we do some treatment, okay? Now, let's say here, we do some treatment so we can increase the peak current, for example. Okay, now, we can do it again. Now you can see the current increase, right? Now you can see right now, this is, the peak is increased. And of course, the slope, you can also see the increase, right? So that's what I show you, the online statistic. Now I want to show you one more thing about the user list. Okay. Now for the user list, what I want to show you is that, okay, you go to here for the user list. So right now you can see here, I have 100 and then 100 milliseconds. I want to user list this one. Okay, user list, and I can select for the epochs A duration. Okay, I want to type 20 millisecond and 100 millisecond. I want to have the repeat here. Okay, and I hit OK. Now I don't want this one right now. Okay, I want the full screen. Now if you go back to see the waveform, you can see here, before it's 100 milliseconds, but now it's list. It's controlled by what setting here, 20 and 100 milliseconds. Now what I mean is that if you click here, the first come here, second go to here, first and here. So basically, if I can do this one, you will see more clearly. So you can see I can customize the changings of the duration. Okay. Now, of course, you can also make it more challenging. Okay. You can type, for example, 10, 20, and then you can also go to 90, and then come back to 4 to 30, 40, 50, 60, 70, 80, and 100. Just give you an example, and hit OK. When I do this one, and you can see, go to 90 and come back to here, right? So I think this one is very, very useful, right? Okay. Now, and then I can also go back to here. I can change for the voltage for the holding level. The holding level is at a B, just like here, because before I voltage give 100 millivolt in here right now. Okay, now you will see something like this: 10, 20, right? 90, right? Right. Okay. Now the last one I want to show you is that I want to give you here is that so here I want to give a file here, and then I have step and step. I want to give a pair pulse 150 and a 5, and then I want to give the variable of the interpulse interval. I set here, okay, so that I can go to here, user list for the duration here, okay. So after that, you see here the user list, the pulse between this pulse, the interval changes. Now, okay, now the thing is that it's too long. I need to change to 50 here. Okay, now you see what I'm talking about. You can see here. Right. Right. So I think using the user list, I think there's very useful features that allow you to customize your protocol. I think I'll run out of time, and I would like to pass the ball to Ed so that he can talk about the Metamorph and also talk about the synchronization of these two software. Okay, Ed, I change the ball to you. Ed, are you ready?
Yeah, I'm ready. Just now getting started here. So.
Right.
Okay, so what we're going to look at for my end as far as the synchronizing of the electrophysiology and the imaging studies with the Axon pCLAMP and the Metamorph software. So lifestyle research is increasingly in need of employing complementary data collection between both the simulation and the image acquisition between the two processes and with the data acquisition that you have. So what we're going to look at is ways of syncing the stimulation with the pCLAMP along with the image acquisition within Metamorph. Before we get into that specifically, there are a few things I just would like to talk about Metamorph as far as some of the capabilities of what it can do outside of just this that type of protocol. So the Metamorph software is a microscope automation and hardware control. It will do image acquisition as well as image analysis. So there's a variety of analysis tools available, and we'll see a few of those in a second. So from a hardware control standpoint, basically the supported hardware that the Metamorph can control includes microscopes, cameras, stages, wavelength changers from like filter wheels to monochrometers, as well as Z device components. And the usage type really kind of dictates how they're controlled within Metamorph, whether it's a stage, focus, illumination, magnification camera. And then you also have a consistent user interface for different hardware. So that's one of the advantages of the software, is that you can have a microscope by one manufacturer, a stage by another, the filter wheels by a third, a camera by a fourth. Instead of having multiple pieces of software to manage to control all those different components, you have one user interface, one software to be able to handle that. So that is one of the advantages of Metamorph, is that it has a large list of hardware that it does control. From the image acquisition side, you have the simple image acquisition from just snapping pictures, and that's what this Acquire dialog does. Display tabs handles most of the scaling for setting how the images are displayed on the desktop. The Acquire tab is where you would set up for synchronizing the shutters for controls of what illumination settings, light that's going to the sample, as well as your auto expose settings. The Correct tab, you can do background subtraction, shading correction, flat field correction, shading correction is the same. So you can correct the images as they're being acquired. The Annotate tab, you can save information with each image, and what's listed in the Annotate tab is what gets saved with the image. The Special tab are device-specific settings, so depending on which camera you have configured, there'll be controls within that. And then additionally, we have the Live Replay option, which is like what we call our Metamorph DVR. So it's ability to record a live event, so you're looking at something happen live and you're not sure when the event is going to happen. Instead of taking really long time lapses with, 90% of that is basically just non-information, or like the baseline events that are happening, you can set up the live replay to record, say, 100 frames, and once it fills up that buffer of 100 frames, it'll start dropping off the last frame and add in a new one. So you have whatever the last 100 frames were, and then you hit a key button, F11, then it'll start recording. So it'll keep the last 100, then it'll record the next 100 frames. So it's a way of more or less getting a snapshot of events that are happening that you may not necessarily know when they're going to start, but you can trigger the full record just by hitting a button on the keypad. Other types of acquisition that can be done is scan slide. So if the box represents a field of view and the overall image here represents maybe your entire slide, you can do what's called a scan slide. So you can snap a sequence of images in a specific pattern in order to then be montaged back together to create one large image of multiple fields of view. So you end up with, at acquisition, you end up with a montaged image that's at a lower resolution. Then you can either produce the entire image or a sub-region and get a high-resolution stitched image as a result from that. So you can do, like I said, basically different fields of view that will eventually be stitched together with multiple wavelengths capabilities within the scan slide. Multidimensional acquisition is, you can do time-lapse, multiple stage positions, multiple wavelengths, Z-series, streaming we'll talk about in a second, as well as execute journals. And that's all, the journals is our automation process within the software. So it's all possible to do at the same time. So you come in, it's a tabbed approach similar to scan slide. You specify which parameters you want to acquire from time-lapse, stage positions, Z, wavelength, and so forth. You specify those specific parameters for the different stage positions, the different wavelengths, the number of Z acquisitions you want to take, and then you just hit the acquire, and it runs through and starts that entire acquisition sequence for you. So it's kind of something that you could potentially, for longer time lapses, start it and just walk away from it and let the microscope run, and the software is capturing images in the process. Image analysis that's available within the software. So you have from simple to complex a type of analysis tools that are available. So it can quantify how many, how big, how bright, how long, how far two objects are apart, and what shape. You can measure colocalization. You can also look at some of the advanced application modules we have are phases in the cell cycle, tracing and neurite processes, look at spine quantitation, fiber tracing, live dead assays. We also have analysis tools for doing FRET, so you can do fluorescent resonant energy transfer calculations, as well as the other thing we don't talk about is, or it's not on this list, are motion analysis, so looking at how objects change over time. You have tools available for that. So from the simplest, a line scan, so you can measure its intensity profile along the length of the line. So if we look at the line here, the graph represents the intensities along the points of the line, so we can see, in this case, our individual cells are showing up as larger peaks across the length. You can also look at this and see that this image in particular is brighter on one end and darker because the overall background levels do decrease over time across the length of this line, so we can also tell how flat our image happens to be for that. The integrated morphometry analysis, this is kind of the one stop shopping for Metamorph, the way some people explained it, is it can do several different types of parameters measured at once. It uses a threshold to identify your object of interest. So threshold is just an intensity mask that's placed on the image. So based on the intensities of your object, you set a mask for that with the threshold, and then it looks for a contiguous threshold to identify an object, and then it will measure those objects based on the threshold setting that you have. You can teach it by clicking on the objects on the image, and then it will set the parameters that you may want as far as from a filter standpoint to be able to filter out certain objects. The other advantage is as you click on the image, it highlights in the data table that is produced. If you click on the data table, highlight in the image so you can easily reference objects to measurements that way. You do get a summary list of data, and there are a variety of other graphs that are available for the integrated morphometry analysis from you can do a scatter plot and a histogram display with that. So this is just a scatter plot reference, and then from the scatter plots you can set up in and apply filters for specific parameters, so you can, again, exclude out certain measurements based on the filters that you've applied for those specific parameters. We do have application-based analysis tools. This happens to be the cell cycle, because it will use the intensity of the DNA to determine more or less what cycle, what portion of the cell cycle it happens to be in. So you can look at things for typically for cancer research is where you'll see, any disruption in the cell cycle is good indicators of cancerous cells. And so, but there's also a variety of other tools, from just the simplest of count nuclei, which is just measuring single cells, to the cell cycle being somewhat more complex. We also have like a micronuclei analysis tool. There's neurite outgrowth. So there's about 14 different application modules that are available. So these are application-specific type of analysis tools that have a large list of different parameters that we'll measure. You can get field data as well as normalized data. So like a granularity module, you can actually calculate the number of granulars per cell in that process. So there is a variety of tools available for that. So not only does Metamorph have and support a large quantity of hardware, it will do the acquisition from very simple single image acquisitions to a time-lapse acquisition to a Z-series acquisition to a multi-wavelength acquisition. But then you can use the multi-dimensional acquisition to combine all those together into an acquisition sequence, or you can use the scan slide to look at a larger field of view image acquisition as well. And then there are a large list of analysis tools that are available for that. So it is, in essence, it is a complete package for what you may need for any type of image acquisition and analysis. So getting back to our specific application, in this case of synchronizing the pCLAMP data recording along with the Metamorph image acquisition. So the hardware setup, you'll start with the multi-clamp and the digidata configured, and you will need to connect the BNC cable of one of the digital outputs of the digidata to the trigger in connector of the camera. So the camera has to be able to support a trigger input signal in order for this process to work. So you would have to check with your camera manufacturers to make sure you have that capabilities. In this case, this is a photometrics camera, so it's a specific camera or cable that will plug in. Then there's a trigger in BNC that we connect directly to an output, digital output on the digidata in this process. So configuring Metamorph to initiate the image acquisition on a pulse from pCLAMP. So this is a process where we're going to set up Metamorph to wait for a pulse that's received from pCLAMP in order to start the acquisition. So getting a little more detail within this is the acquire dialog. First off, we're going to set the exposure time, which is the duration that the camera is going to be collecting photons. It's going to be used for each image acquisition. The next is we specify the camera area, so how much of the chip are we actually using, whether we're going to do full chip acquisition, center quadrant, which is the center 1/3, more or less, or 1/4 of the chip, or we can specify an active region and then only acquire within that area of the chip. Binning is a way of summing pixels together, so it will sum adjacent pixels. So a bin of 2 by 2 is going to take 2 pixels in the X, 2 pixels in the Y, and sum those values together and produce a single pixel. So this is a way of reducing your exposure time, so you're going to gain speed in that sense that you're not exposing the sample for as long of a time, so you can acquire faster. You're acquiring, needing, in essence, less lights, because you can reduce your exposure time, so it's less photo bleaching that can happen to the sample, but it comes at a cost of spatial resolution. So you're losing, you're down to, on a 2 by 2 bin, you're down to 1/4 of the original size, because you're summing 4 pixels together. A 4 by 4 is 16 pixels together, and 8 by 8 is 64 pixels together. So binning has benefits that you can do faster frame times, exposure times, shorter exposure times, and you get smaller image files for storage, but you do lose spatial resolution in the process. The special tabs where you will come in and set the digitizer speed on how fast the data is being transferred off the camera. You would also come in and set the gain setting, which is kind of the amplification of the signals that's there, are pretty much the two main things that you'll be setting in the special tab for the acquire. So once you have the acquire dialog set up, what we're going to look at here is how the acquisition sequence, in essence, works within Metamorph. So the first is you send the acquisition parameters to the camera. You're going to open the shutter, set the illumination setting to the current, expose. This is the exposure time. You're going to transfer the image to Metamorph. You're going to display in an image window. And how can we optimize this for faster performance? Well, if we actually preset the camera up, have the shutter already open before we start acquiring, that's less time that we'll need to start the sequence. And then it's a matter of exposing and transferring that will optimize your speed. So the process for this is called streaming. So it captures images at the maximum rate provided by the hardware. We do have the ability to do device streaming, but you need fast devices in order for that to happen, because we actually tell the device to move when the image is being read out from the camera. So we're also expecting the device to be there. So if the device can't move within the time that the readout of your camera, you can't do device streaming because it won't be in sequence for the acquisition. You can stream to hard drive because you stream for longer periods of time. The data can accumulate on fast hard drives. So, because in order to do a stream acquisition, if you're streaming to RAM, you're limited to half the RAM because it has a storage and then has to transfer from the storage into the display on the desktop. And so you're limited more or less to how long of a stream you can acquire when you do stream to RAM. But if you go stream to hard drive, then you can do longer time periods, especially with the larger hard drives that are available. You have a stream preview, which during stream is a kind of a pseudo-live, so you can update the image window as it's streaming to kind of see what's going on. There's ways of changing how often that update happens for that. So you have those configurations. So in the stream, first thing you choose as far as the acquisition mode, whether it's stream to RAM or stream to hard drive, you specify the number of frames. If you're not doing wavelength streaming, then you're wanting to come in and do just a single illumination setting, a single wavelength. It comes in, tells you based on the number of frames you're acquiring, how much memory that's going to take, how much memory is available. If you set the stream too large, then to the number of to the amount of RAM that you have available, you'll get a warning sign. You won't be able to do the acquisition. There are some cameras, especially frame transfer cameras. You have overlap versus non-overlap mode operation. So in non-overlap mode, you'll do expose and then readout. And then as fast as you can go is the combination of the exposure time plus the readout time. That's as fast as you can acquire it in the images. So overlap mode, you expose and then read out, and while you're reading out that frame, you start exposing the next frame. So it's going to be whatever the longest of the two of the exposure time or the readout time will determine how fast you can go at that point. So this does affect sampling frequency, especially in live cells if things are moving. You may need to look at going to an overlap mode. But again, this only works for a frame transfer type of camera. Storage issues to consider. Stream to RAM is limited to the amount of RAM that you have. If you're a 32-bit operating system, you're limited to 4 gigabytes of RAM on the system. The hard drive space is much more plentiful. It is a bit slower to write to hard drives. You do have the ability to set up more or less a buffer when you're writing to a hard drive to control more or less, because it's a RAM buffer, so images are acquired to the buffer and then written out. So if they start acquiring faster than what the hard drive can keep up, you're not going to be losing frames in that process. So for image acquisition mode, so looking at the camera parameters, if you're wanting to do the acquisition while receiving just a single pulse from pCLAMP, you have to set the camera up in the acquisition mode to acquire images from the first trigger. So you select that, and then you set up in pCLAMP to send a single pulse, and then once that you hit acquire, the camera is going to sit there waiting to acquire images until it receives that first pulse. Once that signal is received, Metamorph will go in and acquire the designated number of frames that you have specified in the stream dialog. If you wanted to do acquisition mode in multiple trains where it acquires at each pulse, and you can set the duration for the pulses, so you can kind of determine how fast you're going to be acquiring. In this case, you need to change the option now to acquire images for each external trigger, and then it's going to sit there and wait to receive a signal, and then once it receives a signal, it acquires and waits for the next signal to acquire, waits for the next signal to acquire. So you need to set up at least to send the same number of pulses as the number of frames as you have designated on the acquire portion of the stream acquisition. So looking at just kind of, again, the highlights as far as what's available with the software, you have full complement of various FRED acquisition, analysis protocols, a variety of other processing and quantitation tools for things like co-localization. You have specialized application modules, neurite outgrowth, neurite tracing, fiber tracing as examples. There are hundreds of different software, hundreds of different hardware that is available that we do control, that we have drivers for. We also have another software package called Metafloor. This is our intercellular calcium ratio image package. So if you're doing any kind of calcium ratioing or pH calculations, or even FRET, because the Metafloor can handle FRET image acquisitions more or less real time. That's a decent software package to look at for that. And that is all I have. So let me stop sharing my desktop, and then I'll pass it back to Jeffrey. So, Jeffrey?
Hello? Hey, sorry. Let's go to the Q&A section. Sorry, I just unmute myself. Okay. So I have a couple questions. One is a question for the pCLAMP. One is for the Metamorph. For the pCLAMP, is that with online function, is it possible to monitor membrane tests during recording? The answer is yes. Yeah, today I don't have the time to talk about this wonderful feature in pCLAMP 10. Yes, you can use, because in pCLAMP 10 there's a feature called membrane test between sweep. Now remember that it's only in a pCLAMP 10 version, not in earlier version. Okay, so you can use that for online statistic function for the membrane test. Okay. Ed, I have a question for you for the Metamorph. Now you talk about how to trigger, to synchronize these two software by using pCLAMP to trigger for the Metamorph. Is a way that we can use the Metamorph to trigger for the pCLAMP?
That is correct. As far as the camera cables that use the ability to have an input trigger also has an output trigger available to it. So in essence, you would kind of reverse the process for this. Instead of setting Metamorph up, waiting for a signal, you would set pCLAMP up, waiting for a signal, and then once you start the acquisition, at each acquisition, the camera will send out a pulse on the trigger output, and it'll go into the input on the digidata, which the pCLAMP will recognize at that point, and then start its recording after that. So this works in both directions. So you can configure the software up to either wait to receive a signal to do the imaging or to send a signal at each acquisition, which the pCLAMP software will recognize and then begin its recording.
All right, I think we run out the time. So I think this slide I just want to show you that so if we still have some questions that people can still send it in, so we don't have time to answer all the questions, but I will open for another 5 minutes so that you still can have time to type in the question. Okay. Now, before we close today, I want to let you know that if you want to view our previous recording webinar, please visit molecular.webex.com, and then you can select list of the event at the left-hand side, and then you select for the getting the most out of the pCLAMP series, and you can access to all previous recorded webinar. For today's webinar, it will be posted maybe at the end of this week. All right. So once again, I would like to thank you for all your attention today. So, and have a good day for everyone. Okay, goodbye.